Hi, welcome to video notes 12. This is about determining the features of rational functions from an equation. In Ms. White's video, you probably saw these features on graphs and were able to pull some of the meaning you'll see here from those graphs and from the factored forms of those rational functions. So we're going to explore those a little bit more here, and I have a table that you might have seen before in some form or fashion. If not, it's a good summary of the things you found in this section of videos. But we'll be looking at x-intercepts, y-intercepts, vertical asymptotes, holes, and the domain of rational functions. For the holes and vertical asymptotes, those are examples of discontinuities. And if we were just pulling up y equals 1 over x as our token example of a rational function, if I'm drawing a sketch of it on an axis, just a real quick thumbnail sketch, we can see that there's clearly a discontinuity where x equals 0, the graph is broken into two separate pieces, left and right side. Discontinuities are characterized by undefined points. So we have a double whammy with the vertical asymptote there on y equals 1 over x, which is the parent function for rational functions. There is not an x, or like there's a missing y value at x equals 0. And the graph is split in two, and the y values of that graph go to two separate ends of infinity. The top goes to positive infinity with its y values, and on the left side of 0, the y values go to negative infinity. So that is a prime example of a discontinuity. And again, holes and vertical asymptotes are discontinuities with these rational functions. Now, this chart might seem a little bit overwhelming, and I find that whenever I put in something like this, I get a lot of like nervous looks, and the generic factored form of rational function does not need to be memorized, but I am going to use it to show you where these features appear in the equation. So first off, we're looking at x-intercepts, and you should have something to either highlight or like underline or box with yourself, so maybe a different color, something that sticks out for these notes. And the x-intercepts come from the numerator. So we're going to set our numerator equal to 0. And that's because we set y equal to 0. So if we set y equal to 0, you don't have to write this, but if we set y equal to 0 and we try solving for x, we actually end up multiplying all of these factors over to the left side of the equation. And what that does is, since we're multiplying by 0, it gets rid of all these factors. So really, this simplifies down to be setting the numerator equal to 0. So in our equation, we know how to set factors equal to 0. We know what makes each factor equal to 0. That's going to be positive a and negative b. And that's in our generic result for this. So if you have actual numbers, you'll know how to interpret this. But if we move on to y-intercepts, I have the multiplied out form of this rational function. So we do not want to use the factored form when we're finding the y-intercepts. And to find where to look at the y-intercepts, we're going to use negative ab and negative a squared c. So it's our last terms. It's the last constant terms. I'm going to make a little note there, last constant terms, in the numerator and the denominator. So we're going to set our x variables equal to 0. So if all of these x's are 0, 0, 0, 0, 0, 0, 0, then we can figure out what our y value is. So here we have something a little nasty that comes out as our generic result, but it's going to be pretty easy to work with since it's just a couple numbers. We'll have negative ab divided by negative a squared c. Our vertical asymptotes are going to come from the factors in the denominator that do not have a shared factor in the numerator. So they'll come from this term, x plus a, and x minus c. Because x minus a and x minus a divide each other out, they do not represent x minus a, that factor does not represent a vertical asymptote. So we'll set the factors that we've found equal to 0. And we should specify and say factors not divided out. And you like to say cancel, maybe, but not divided out is what I'm going to say. So here, x is going to equal negative a, and x is going to equal positive c. For our wholes, we are going to use the divided out factors. So one is factors divided out, one is factors not divided out. So we'll still set those factors equal to 0. So x is going to be just a. And then our domain, we're going to look at the discontinuities. Which are, again, our vertical asymptotes and wholes. And we have to state our domain from left to right. So we're not really sure what they are for this, but we'll just say since C is I guess a further number in the alphabet, it'll be a bigger number. So it doesn't quite matter because we're using negative a and positive a, not negative c. But anyway, negative infinity to negative a, which is an x value, and then negative a to a, and then a to c, and then our last interval, it might not fit so well, c to infinity is going to be our interval notation for the domain. So we have 3 breaks in the domain, and you can see them right here. There's a break at negative a, break at a, and there's a break at c. So again, just to drive this home, negative a is a vertical asymptote, a is a whole, and our last vertical asymptote is at c. And that's just from this information we found by factoring our generic polynomial here. Now if you'd like to look more at this graph, I'm going to leave this in PDF form, and you should be able to click on this Desmos link and it'll take you to some discovery questions about that. So what we're going to do is we're going to find those 5 things for each of these rational functions. I'm going to factor them and determine those 5 things, and if I were you, I would pause, factor them, and then maybe follow along as we go through the 5 things we've discovered from each. Before I show you the rest of them, for the x-intercept, if we set the numerator equal to 0, we get x equals 0. But you'll notice a contradiction between the whole and the x-intercept. If we have a whole at x equals 0, which, again, that means we set this x in the denominator equal to 0, then that's going to produce an undefined value. So we have a whole there, but that means we actually don't have an x-intercept. Where our x-intercept ought to be, we have a whole. So this is not true. We are actually going to say we do not have an x-intercept. Alright, and I'll show you the results if you want to pause and try the rest of them. Here we are with the full results from factoring these and looking at the characteristics. So let's start with 2. In this one, we don't have any x-intercepts because we cannot set 1 equal to 0. We can't set the numerator equal to 0. And then with our wholes, we don't have any common factors between 1 and x plus 2. There's nothing to factor even. So that might be the confusing parts with this one. And with our y-intercept, I just set x equal to 0, so I had 1 over 2. And with 3, I factored that. Our x-intercept, you'll notice, is not there. Even though we've set the numerator equal to 0, we have the same situation as number 1. The wholes are at the same factors that produce zeros in the numerator. So we don't have any x-intercepts. And we also don't have a constant term in our denominator, so we can't have a y-intercept. For number 4, we also don't have a constant term in our y-intercept, so there is not one. But we can find an x-intercept that is not shared in our denominator. So you see how much of this is just comparing numerator and denominator factors and knowing what yields what. And we can do this without using a graph, and I think that's the key point here. So thanks for watching, and I'll see you all later. Bye.